So in this video, we'll be talking about drawing lots of tree diagrams and then the fundamental counting principle. It's section 11.4. So let's talk about a tree diagram. So let's say it's early in the morning, you're super groggy, and you've got to pick something to wear. And you have not done your laundry lately, so you only have two pairs of jeans. You've got some blue jeans, blue jeans, and some black jeans. Okay, and you only have three pairs of t-shirts, white and green and red, that are clean. Let's talk about how many outfits you can make. So when you're wearing your blue jeans, you could then wear a white t-shirt, you could wear a green t-shirt, or you could wear your red t-shirt. So with blue pants on, you've got three outfits. And then you could do the same thing with the black. You could have white, you could have green, or you could have a red shirt. So 3 here and 3 there. So your total would be 6 outfits that you could wear. Okay, so this is called a tree diagram because it's got branches. Yeah. And it's used to show all the different possibilities, okay? So we had 2 pairs of pants, we had 3 shirts, and the number of outfits we had was 6. So we had a 2, we had a 3, and we got a 6. How could you get a 6 out of a 2 and a 3? We could just multiply them, right? Multiply. So that's what the counting principle is. So if you can do one thing 2 times and the next thing 3 times, the way you could do them together is 2 times 3. So that's what this counting principle is saying, is that you're going to multiply those 2 numbers together. So we don't have to always make a tree diagram. You can just multiply now that you know what to do. So you're at the Greasy Spoon restaurant and you can have 6 appetizers. You got choices of 6 appetizers and 14 main course meals. So how many ways can a person order a 2-course meal? We could have your appetizer, we could have 6 of them, and your main course, you could have 14 of them. So 6 times 14 is going to give you 84. You could have 84 different types of meals at the Greasy Spoon. Or let's go to Bubba's Barbecue. And in this case, we had 10 appetizers. So the number of appetizers was 10. And the number of main course meals is 15. So how many ways can you order a 2-course meal? Multiply those. There's 150 different ways that different meals you could order, right? Here's some more. You are an Associates of Arts major, and you have to take psychology and then another social science course, okay? It's March 15th. Actually, it's sort of close to that. SEC's fall classes just opened for registration. Since you're registering early, there are 15 sections of psychology and 9 sections of social sciences that are still available, and they do not conflict with each other. So how many different 2-course schedules could you make? So you've got your psychology, you've got 15 sections you could choose from, and your social sciences, you got 9 sections you could choose from. So when we just multiply those together, we get 135 different schedules, ways that you could make your schedule. Okay. So now let's go back to our little dude who, remember, he already had his blue pants and his black pants, and we've got our 3 shirts. But now we've got 2 different kinds of shoes, so that could change how many outfits we have. So we've got our blue pants, and we would have a white, a green, or a red shirt. And then if you did blue pants and a white shirt, you could then choose between black and gray shoes. Same thing with a green shirt. You could have black or gray shoes. Red shirt, you could have black or gray shoes. So now, and with just wearing your blue pants, you could have a total of 6 outfits. All right, just with the blue pants. Now, what about the black pants? We could do the same thing. We could have my white shirt with my blue and gray pants. We could have my green shirt with my blue and gray. I said pants, but I meant shoes. And I could have a red shirt with blue and gray shoes. So I've got 6 outfits here. So my total number of outfits, if I add them all up, is 12. Right? So we had 2 pants, we had 3 shirts, and we had 2 shoes. And we made 12. Just like we did before. You could just multiply all those together. 2 times 3 times 2 to get that how many outfits we have. Okay. So that is actually, once you start stringing all these together, you come up with the fundamental counting principle. So this is what it states. The number of ways in which a series of successive things can happen is found by multiplying. Right? By multiplying the number of ways each individual thing can happen. Okay, so we're just going to multiply them all. So you actually did laundry and you just love clothes. So now you have 30 pairs of jeans. 30, not just 2. 30 pairs of jeans. You got 20 t-shirts and you got 12 pairs of sneakers. How many choices would you have now? Well, again, we just take my 30 jeans and my, not 12, my 20 t-shirts and my 12 sneakers. Just multiply all those together. 7,200 outfits. That's a lot. Yeah, I would never make you draw a tree diagram with that many outfits. Okay, so let's talk about Mama Jane's Pizza Joint. Okay, she has 2 choices for sizes. You could get a medium or a large. She has 3 choices for the kind of crust you can have. You could have a thin, a thick, or a regular crust. And she has 5 choices of toppings. Okay, so we want to know how many different 1-topping pizzas she could order. So we're going to do, remember, we're going to have our size, we're going to have our crust, and we're going to have our topping. So we had 2 sizes to choose from, we had 3 crusts to choose from, and we had 5 toppings to choose from. So we could have actually 30 different kinds of pizzas. 30 different 1-topping pizzas. So now we're going to have a 2-topping pizza. Okay, and you can double the topping. So in other words, you could have double pepperoni, right? So we still have 2 choices for our size. We have still have our 3 crusts. We still have 5 for topping 1. This is my topping 1. And then topping 2, I've got 5 choices there also. So I'll multiply all those together and I could now get 150 different 2-topping pizzas. Okay. So now let's say you are working for BMW. So they're experimenting with their lightweight 3-wheel cars designed for 1 person and it's considered ideal for city driving. So you want to order one of those cars. And so let's talk about how many ways you could order that car. You have colors. So you've got 9 colors. You can have with or without air conditioning. So you have 2 choices there, with air conditioning or without. You can have electric or gas. So there's 2 choices there. You could have with or without an onboard computer. So you've got 2 choices there. So all I have to do is multiply all those together. 9 times 2 times 2 times 2. So that's really like 9 times 8. So that's 72. So we could get 72 different kinds of cars. All right. You are taking a multiple choice test. And that test has 10 questions. And each question has 4 answer choices. So A, B, C, D. Each one has 4. With only 1 correct answer per question. So we want to figure out, if you select one of these 4 choices for each question and you're going to leave nothing blank, how many ways can you answer the questions? So there's 4 ways to answer number 1, A, B, C, or D. There's 4 ways to answer number 2, and 4 ways to answer number 3. And for all 10 of those, there's 4 ways. So I'm going to multiply all those together. So that would be what, 4 to the 10th power. And you could put that in your calculator, 4 with that little caret, or you might have y, x. Either way, you should get a whole lot. What's that, 1,048,576 ways of answering that question, okay? Or answering all those questions, that multiple choice quiz test. All right. So now we've got another multiple choice test. It's got 6 questions. So 1, 2, 3, 4, 5, 6. Each question has 3 answer choices with only 1 correct. So I would have 3 choices here, 3 choices there, 3 there, 3 there, 3 there, and 3 there. So that's the same as 3 to the 6? 3 to the 6th. When you stick that in your calculator, you get 729 different ways that you could answer that 6-question multiple choice test. Okay? So we're going to start getting a little bit tricky, okay? And as we get trickier, it actually is more applicable, okay? So here we are. We've got, you have the letters A, B, C, D, and E are going to be used to make a 4-letter ID card. So it's just 4 letters, and we're going to mix them up, right? So we're going to see how many different cards are possible if the letters are allowed to be repeated. In other words, I could have A. That could be one of my choices. Okay, so how many do we have? 1, 2, 3, 4, 5. So we have 5 different letters we could choose. So we have 5 choices for the first one, 5 for the second, 5 for the third, and 5 for the fourth. You just multiply all those together. That's going to be 5 to the 4th. Plug that in your calculator. 625 different ID cards. Okay. Now, let's say that you can't repeat it. Okay. Each letter can only be used once. So now we still have my 4 ID cards. Okay. And we have A, B, C, D, or E that we can choose from. Notice the very first one, I've got all of these I can choose from. So I get 5 choices. So now let's cross one of them off. Let's say I chose E for that one. So now we only have how many left? We've got, 4 choices? We only have 4 choices now. All right, and now I chose C. Now I've only got 3 choices left. Say I chose D. Now I only have 2 choices left. All right? And then I'm done because I only had 4 on my ID card. So that is going to be 5 times 4. That's 20. And 3 times 2, that's 6. 20 times 6. So we've got 120 choices. So notice when you don't have repeats, it definitely limits how many you can use. So let's say you have a lock on a storage unit. and it's controlled by a keypad that has 6 digits, 1 through, let's see, oh, it's containing digits 1 through 3. I mean, 1 through 5, sorry. Woo, I need to be able to read. Okay, how many 3-digit codes? So that means 1, 2, 3. We got 3 digits, and we've got 1, 2, 3, 4, 5. That's what we can choose from. Okay, and these can be repeated. So I have 5 choices for the first one. I've got 5 choices for the second one and 5 choices for the third one, because even if I chose number 1 for the first one, then when I get to the second one, I could choose 1 again. So 5 times 5, that's 25 times 5. I've got 125 possible codes. Okay. Now let's say we cannot repeat it. So I start off with 1 through 5 I can choose. So I pick one of them. So I had 5 choices. Let's pick 1. Now, how many choices do I have left? Since I can't repeat, I only have those 4 left. And we'll pick the number 2. So now I only have those 3 left. And I'm done. So that's 20 times 3. So I've got 60 choices. Okay. Now, just recently, I think, this month? I can't remember when, but in the upstate, you now have to start dialing the area code. Do y'all know that? Like if you want to call your friend now, you can't just dial their number. You have to dial 864, okay? Because we've run out of numbers because so many people are moving here. So they've started a new area code. I think it's 810, I think. Anyway, anybody new that comes into the area, when they get a phone number, they're going to get an 810 area code. I'm not making this up, y'all. Just for this problem. This is a true story. But anyway, it says telephone numbers in the United States begin with a 3-digit area code followed by 7 telephone numbers. Now, I didn't realize this, but area codes and local telephone numbers cannot begin with 0 or 1. So this one here and this one cannot be 0 or 1. Not be 0 or 1. Okay, just those 2. They want to know how many numbers are possible. So we've got, let's look at all our numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've got actually 10 numbers we could choose. So at the beginning, it can't be, right? It can't be 0. It can't be 1. So we have, let's see how many we have left. We've got what? 8 numbers left. Okay. So this one and this one is special because it can only have 8 numbers. Because both of those cannot be 0 or 1. But the rest of them, like the second one here, this one I can choose from any of those. So I have 10 choices, all right? And notice it didn't say that it could not repeat, right? So I can have 10 choices for each of these other ones, right? Each of these others, I have 10 choices. So I have 8 times 8 is 64. And then I have, let's see how many zeros. 2 zeros there and 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 plus 2. So I have 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And that's what you would get if you multiplied all those out. Is that right? 1, 2, 3, 4, 5, 6, 7, 8. Okay. I put this guy in the wrong spot. Sorry. 1, 2, 3, 1, 2, 3, 1, 2, 3. There we go. So that's how many numbers that you could possibly use. Y'all, that is 6 billion? And we ran out? Anyway, we got a lot of people coming. Okay, here's another one. At the SEC Deli, each lunch special, we don't have a deli, by the way, each lunch special consists of a sandwich, a salad, and a beverage. The sandwich choices are roast beef, ham, and turkey. So the sandwich is roast beef, ham, and turkey. And the salad choices are macaroni salad and potato salad. The beverage choices, is coffee or soda, okay? Use the counting principle to determine the number of different lunch specials. So we had, how many sandwich choices do we have? 3 sandwich choices right there. 3 sandwiches. And we had 2 salad choices. And we had 2 beverage choices. So when I multiply those together, I should get 12. Now they want us to construct a tree diagram that proves that number, and they want us to list the sample space. Whew, okay. So I've got my sandwiches, and we got my salads, and we got my beverage. Okay, so we're going to start off with what? Roast beef. And we can choose between, what did we say up here? Macaroni and potato. And then my beverages were coffee and soda. Yeah, coffee and soda. So, and then I could do potato salad and have coffee and soda. So with my roast beef sandwich, I have 4 options, 4 total choices for my whole lunch. Okay. Then we had ham. Ham was next. Got our ham, and we could have macaroni or potato. Goodness gracious, potato, and for beverage, coffee and soda. And then the last one was what? Turkey. Got a turkey. Same thing. Macaroni, potato, coffee, or soda. All right, so now we are going to, so we made our tree diagram. So make a tree diagram. Yep. And then list the sample space. So the sample space. So basically you're going to follow one branch all the way to the end. So this guy, I'll just highlight it. So that guy, I have a roast beef with macaroni and a coffee. Or I could have roast beef, macaroni, and soda. Roast beef, macaroni, and soda. And now let's see. I'm going to go this way. Roast beef, potato salad, and coffee. Roast beef, potato salad, and coffee. And then roast beef, potato salad, and soda. All right, and then we go and do the exact same thing with our ham. Ham, macaroni, coffee. Ham, macaroni, soda. Or ham, potato, coffee. Ham, potato, soda. So that's all my ham lunches. And now let's do turkey. Turkey, macaroni, coffee. Turkey, macaroni, soda. Turkey, potato salad, coffee. Turkey, potato salad, soda. Let's add all those up and see how many we got. We got 4 there, and 4 there, and 4 there. So sure enough, that is 12. So we actually do have 12. Okay. So we've done letter B. Right? We've done letter B. Constructed a tree diagram and listed the sample space. So this is my B. Now my C says we're going to draw somebody at random and determine the probability that a roast beef sandwich and soda are selected. Let me do that in maybe brown. Roast beef and soda. All right. So it doesn't do me any good to go down here to the ham and the turkey because they said I need roast beef. So I need roast beef and soda. So here's roast beef. That one's coffee, so that doesn't work. This one, that one is roast beef and soda. And that one is roast beef and soda. So the probability of a roast beef and soda is 2. I just had 2 of those out of how many total did we say? We had, we had 12 out of 12. So that would be 1/6 is my probability. Let's look at another one. This one says, what is the probability? Let's do gray. What is my probability of, determine the probability that neither macaroni salad or coffee is selected. Hold on. I thought I did it here. Sorry, y'all. Okay. So that neither macaroni salad or coffee. Okay. So it cannot have macaroni and it cannot have coffee. So it has to have potato salad and soda. Potato salad and soda. So that will be that guy. It'd have to be the same thing here. Potato salad. Yeah, potato salad and soda. So that guy would work. And potato salad and soda. So I think it's just going to be, 3 of them? So the probability of no mac and cheese and coffee is going to be 3 out of 12. So that probability is just 1/4. Right. All right, last one. So we have a bag that has 4 different colored balls in them. All right, so we are going to pick out 2 of those balls, and they're going to be selected with replacement. That's important. With replacement means we're going to stick it back in after we pick let's say we get an orange ball. After we pick it, we can put it back in so we have it to choose from again. So it has a red, 1 red, 1 blue, 1 green, and 1 orange ball. So let's use the counting principle to determine the number of sample points, different possibilities in the sample space. Notice we're going to choose 2 balls. So that's 1, 2. We've got 2. And how many choices did we have for the first one? We had 4 in there when we picked. So let's say we picked the orange guy. Okay. Now we pull it out, record it's orange. Then we get to put it back in. And now we have 4 more to choose from. So we should have 16 in our sample space. Now they want us to construct a tree diagram and list the sample space, okay? And after we list that sample space, we're going to use that to answer some probabilities, okay? So we've got some choices. So the first draw, so this is the first one that we're going to draw, is we could either choose a green or a blue or an orange or a red for the first draw. For the second draw, if we chose a green, we only have blue and orange and red to choose from. If we chose a blue, then we have a green or an orange or a red, right? Because we already had chosen the blue one. If we did orange, we only have what to choose from? We got a green and we got a blue, we got a red. Then the last one, if the first draw was a red ball, we'd have green, blue, and orange. Okay, so let's draw out our sample space. So our sample space says I would have green and then blue for this one. Green and then blue. Green and orange. I want to do that in a different color, sorry. Or in, yeah. Green and blue, green and orange, and green and red. Or we could have blue and green, blue and orange, and blue and red. Blue and orange, blue and red. Or if we chose orange first, we could have orange and green, orange and blue, orange and red. And last, I'll do it in purple, we could have red and green, red and blue, red and orange. And how many do we have? Let's see. You know what I forgot? I'm treating that second draw as if I do not have replacement. So I could have replacement with all of these. So let me go put it back in. I could have a green. I could have another green one. Here I could have a blue one. So blue and green. Blue and blue, sorry. Blue and blue. I'm forgetting my doubles, right? So this one I could have orange and, whoops. I could have orange and orange, orange and orange, orange and orange. And then this one I could have red and red, red and red. So, and I caught my mistake because I started counting and I didn't have 16. I'm supposed to have 16. So now I've got 16. I've got 4 of those, 4 of these, 4 of those, 4 of those. All right, so I have 16. So now let's look at the probability that the red ball is selected twice. So probability that I have RR. Well, I only have one RR, right? That one. So it's 1 out of, how many did we say that we had? We had 16. 1 out of 16. Okay, now let's determine the probability that neither ball selected is orange. So probability that it's not orange. So when I start writing these down, I'm looking for those that do not have orange. So, or I'm just going to circle them. So that one is no orange, no orange. That one has orange, no orange. That one has orange. Not that one, not that. All of these, I'm not going to do any of those, right? Because they're all orange. So that one, and that one, and that one. So, because all of these guys have orange. So let's see how many I circled. 1, 2, 3, 4, 5, 6, 7, 8, 9. I circled 9. So 9 out of, we said there were 16. 9 out of 16 are not orange. I don't believe that reduces. All right. And then the last one of today is determine the probability that the orange ball is selected at least once. Probability that we have orange, okay, at least one time. So let's go back in. I'll circle it in red. Here's one that has orange in it. Here's one that has orange in it. You know, it might be easier for me to highlight. Why don't I highlight? So this one has orange in it. This one has at least one orange in it. All of these have at least one orange in it. And this one has orange in it. So let's see how many we highlighted. 1, 2, 3, 4, 5, 6, 7. So I had 7 that were orange out of, let's make it orange, right? Out of, how many did we have? 16. And I can't reduce that. So now y'all are going to be experts on our probabilities.